All right, guys. So we're gonna start with Kirchhoff rules. Let me see. There you go. So basically, the reason we're gonna need to use the Kirchhoff rules, or Kirchhoff or Kirchhoff, eh, everybody has like a different way of pronouncing this name. So I go with Kirchhoff. So so basically, a Kirchhoff developed a set of rules, basically two very simple rules to solve um, basically circuits that are not simple. That means, for example, so here's a battery. Oh, let's kind of go back. All right. All right, so let's say here's a battery, positive, negative terminals. And let's say you have two resistors in series, okay? Or maybe like there's another, set of resistors here in parallel. And let's say we go like that. All right, so you have maybe 10 ohms, 10 ohms, 10 ohms, 10 ohms. So all of them are 10 ohm resistors. And let's say this is like EMF, right? What we have here is a simple circuit because I can take those resistors and I can add them together in series and in parallel and represent all this with just one equivalent resistance, right? So you can see that those two can be combined into so let's say a single 20 ohm resistor because they're in series. 10 and 10 gives you 20. Those two can be combined into equivalent resistance. So on 10, 10, you can do it, you can do your own calculation, but you have two identical resistors in parallel. Equivalent is half of it. So let's say this is 5 ohms. And then even those two then can be combined to represent one 25 ohm resistance. So you can see, right, that circuit can be simplified to just one 25 ohm resistance. Right. So that's why it's called simple circuit. Well, one of the things we can do here is, for example, what if here, instead of two resistors in parallel, so I have a 10 ohm resistor, but then another battery, an EMF1, EMF2. Well, that means not only you have 10 ohm resistance over there, but you have another battery. How do you do that? Can I add those two then in parallel together? Well, not anymore, because those two 10 ohm resistors are not in, parallel. Remember, parallel means two resistors connected at both sides. Well, they are connected at this side, but they're not on the other side because there's a battery between them. So no longer simple circuit. You can see, right? All I did is just added one battery, but no longer I can have this, right? So this is where the circuits can get a little bit complicated. And Kirchhoff came up with a couple of very simple rules that we can use to, solve this type of problems. So technically, once we go over these rules, you can see that even this circuit is not necessarily that bad. You have no problem solving that once you understand how to work with two batteries or three batteries and things like that. So it's not necessarily that bad. It's not simple circuit anymore. All right, so he gave us two rules. One is known as a junction rule, and we kind of already used that before, or we have seen that before, is that, for example, when things like this. So here's a battery, and there's a positive terminal and negative terminal. Then we know that as soon as you, close the switch or whatever it is, like let's say if you have, there's a current. Here, I1, let's say, is the current coming from the battery. And this, current then gonna flow through the, wires, right? Because you can see we have one path to go, and then come and get to this point. See that this point is a junction point, okay? So the junction point gives you multiple paths. Well, when I1 comes to that junction point, now there are two paths to go, right? So that means some of the current gonna be going through top part, some of them gonna going through the bottom part. So that's why what you get is you get a junction point and you get multiple currents. Okay. Now the you can see in a way what we looked at before here is that I1 comes in and splits into two, right? But the junction rule kind of gives it a little bit differently. It says if you have a junction point, in that case, that particular junction point, if you add all the current at the junction point, so let's say you have I1, I2, and I3, right? So if you do I1 plus I2 plus I3, which is basically sum of your currents, right? Their sum will always be zero, right? So that's, very simple rule, right? So it says you take all the current at that junction point, add them together, you get zero. Well, one thing you can see here is that you cannot get zero if all the currents are positive. Well, current is a scalar quantity, so technically there is no direction involved with that. So positive, negative has nothing to do with direction. Positive, negative have something to do with the direction relative to the junction point. And again, it's not a vector direction, but sort of like, is it going into the junction point or is it going out of the junction point? Because one thing we have here is his rule says that. So add all the currents together for the junction point, you're going to get zero. But doing so, pay attention to the current going into the junction point or out of the junction point. Because any current directed into the junction point, we're going to take that to be positive current. And any current going out of the junction point, that's going to be the negative current. So that's why one thing we have here is you can see that I1 is positive, I2 is negative, and I3 is negative because I1 is going into the junction point, so positive, and I2 and I3 go out of the junction point, so they're negative. So that's why if you add those three together like I have over there, it's simplified to this. I1 positive, so you can see, right, plus negative I2 plus negative I3, which will then simplify into I1 minus I2 minus I3 equals zero, right? So we get that equation simply because current 2 and 3 are negative. Okay, so it's a simple rule, but it's a very important rule. And this should always be one of your equations that you're going to be using to solve those Kirchhoff rule, circuits. Okay, any junction point, you look at the currents, add them together, you get zero, paying attention to the positive, negative for the current in terms of into the junction point or out of. All right. Second is a loop rule. This is also something we have more or less seen before. It tells you that the sum of the potential differences across all the elements around any closed circuit loop must be zero, right? Which means that here's your loop, summing all the potential differences gives you zero. And in a way, this is a statement for the conservation of energy because it considers the potential energy, difference between, two points of circuit elements everywhere in your device. Here's the thing. This works for very simple circuits. This works for, complicated circuits, doesn't matter. So I can take this simplest circuit and I can still apply that. But let me do this. Let me give you an example, more or less a simple example, because one thing we can do here is, so let's say here's a battery, EMF, and let's say here's a resistor. Let's say resistor 1. Here, resistor 2. Okay. And let's say here's then another battery. Okay. And let's say this is your circuit. Then let's call this EMF 1 and EMF 2. All right, so how many circuit elements or how many devices we have in the circuit here? Well, we have 4. We have 2 EMFs and 2 resistors, right? So that means one of the things I can do here is I can say, all right, so then if I look at potential difference across EMF 1, then potential difference across, resistor 1, because let's say I start from here and I look at, okay, here's my device 1, device 2, device 3, device 4, right? So then I kind of go in that order. So then delta V EMF 1 plus potential difference across resistor 1 plus potential difference across resistor 2 plus potential difference across EMF 2. If I add them together, I should get 0. All right. So in a way, the idea is this. So let's say if you start from, see, this is, let's say, point A, this is point B. And then this is point C, this is point D. E and F, G and H. So delta V, this guy over here, is the potential difference between A and B. So technically it talks about that, right? So what is the potential difference between A and B? Delta VR1. So in a way, I can maybe write like this: VAB, potential difference across points A and B, plus delta VR1 VCD, plus delta VR2 is the potential difference across that resistor 2, so VEF, and then plus VGH, and this is equals to 0. All right. So that's kind of what it represents. Obviously, again, as you can understand, I cannot get 0 unless some of those potential is negative. And when is it positive, when is it negative? That's the rule that we're going to be considering in the next few slides. But generally the idea is this: whenever you are going through the battery, so let's say you start from this point A, okay? So when you go from A to B, you're going from negative terminal to positive terminal, okay? And generally it means, as if you remember one of the things we talk about EMF, when you go from negative terminal to positive terminal, your potential increases. Because remember, so this is a battery, right? So negative terminal will always have lower potential than a positive terminal. That means if I'm going from A to B, I'm going to increase my potential. But one of the things that you can see here, what I did is, because I went from A to B, then from C to D, E to F, G to H, I technically considered my direction of this loop to be clockwise, right? So that's why I chose a clockwise direction, and I went from A to B, C to D, right? And basically at the end, I come back to A again. So one of the things we can do here is we can assume there's a loop. So this loop that I'm choosing is this loop over here, and then I choose a direction and I go around that loop. Okay, so now next few slides we're going to then talk about in terms of which one is positive, which one is negative, but try to kind of more or less remember, right? So what I have here is VAB is the EMF 1, VCD is the resistor 1, and then one thing you can also try to remember here is this. So if I have this particular circuit, see, I have EMF 1 and EMF 2, and this is just one path, right? So the question is, in which direction is the current? Is it clockwise or is it counterclockwise? So, because here's the thing, this is positive, this is negative, right? And this one here, this is negative, this is positive. Okay. So what I get here is this EMF gives me current in this direction, which is going to be, clockwise. EMF 2 technically gives me current in that direction too, right? Because this is clockwise. So technically they both give me current clockwise. So then I can for sure say direction of the current is clockwise. But what if the terminals of the EMF 2 were up other way around? So let's say they were, this one was positive, this one was negative. But if that was the case, in which direction would have been current? Well, you had to kind of like figure out by looking at which one is the largest EMF. But at the same time, one thing we could do here is we can just guess a direction of the current, calculate, let's say, using your guessed direction. And if you wanted to calculate the current at the end and you get a positive value, that means you guessed the direction correct. And if you get a negative value for the current, then you just guessed the direction wrong. You just go back and only change the direction of the current. Nothing else is affected but your original guessed direction of the current. So that's why it's very simple in a way that you don't know the direction of the current, just guess. Educated guess, choose a direction, set up your rules, for this loop equation with respect to your direction of your current, right? And then set up your equation, calculate your current. Positive current at the end tells you guessed correctly. Negative means, you just go back and change the direction of the current, and that's all. All right, so in any case, here you can see that since both of those EMFs gives me clockwise current, so then I can for sure say that I'm going to have a current clockwise going from C to D, right, for the resistor 1. I'm going to have then the current again clockwise going from E to F for the resistor 2. And, basically the EMF 1, right, goes from negative to terminal. That means think like this. Look at my loop. If I start from A, right, when I go from A to B, I go from negative terminal to positive terminal for the EMF, okay? And then one thing I can, we'll talk about that, right? So then I can say that VAB is going to be a positive quantity. Why? Because I go from negative terminal to positive terminal. That's the direction of my loop, right? Clockwise. And if I go from negative terminal to positive terminal, I'm always going to increase my potential. By how much is my potential VAB going to be increased? Well, it's going to be increased exactly by this amount of the EMF1. So here I can write this as EMF1. Then when I get to the current, so resistor 1, I have to look at two things to figure out if this potential across resistor 1 or this VCD, right? If this is positive or negative, I have to look at two things. I have to look at my resistor 1, okay? I have to look at how the current going to the resistor 1, which is from C to D, and also look at my direction of my loop, okay? So in a way, you can see that the current goes from C to D, right? At the same time, direction of my loop also goes from C to D, right? Because I chose clockwise direction, okay? And if that's the case, if my loop has the same direction as the current across the resistor, what you get always is a potential drop. So it's going to be minus, because it's going to be drop of potential. And by how much was going to be dropped? Well, I can use the Ohm's law to figure out. It's going to be the current through that resistor time its value. Remember, voltage equals IR, right? So I can use that equation. Again, we'll talk about that, but that's, pretty much what we get. That means if you're going, if your loop direction matches the current direction across the resistor or through the resistor, that means potential will be dropped. Same idea for the resistor too. See, you go from E to F, the current goes from E to F, and your loop goes through to from E to F. That means you're always going to go from higher potential to lower potential. Remember one thing, right? So technically you can see this point C is connected to your positive terminal. That means it has a higher potential than point D, right? That means if you go from C to D, you go from higher potential to lower potential, remember, right? That means you are decreasing your potential. That's why you have negative. That means same way I have a negative potential for VEF, which is across the resistor too. So I get negative I times R2 equivalent of potential difference. So the next is the EMF2. Well, I'm going from G to H. Well, when I go from G to H, I'm going from negative terminal to positive terminal, right? Which means that, again, I'm gaining potential. Like how much the potential gain is there? Well, it's equals to amount of EMF2. I can say that plus EMF2, and that's equals to 0. That means this is then my equation for that loop. That means my potentials are positive for the EMFs, and my potentials were negative for the resistors. And, if I add them all together, I'll get 0, okay? All right, so let's, dive into this in greater detail here. So, all right, so potential energy, remember, so potential is potential energy per unit charge. So, but you can think of it also in terms of potential, right? Potential energy. So potential energy decreases whenever the charge moves through a potential drop, negative IR. Negative IR across a resistor, or whenever it moves in the reverse direction through the source of EMF, as I said, right? So if you go from negative terminal to positive terminals of EMF, you're gaining potential. Your potential energy increases. But every time you go through a resistor in the direction of the current, you're dropping your potential energy. Remember, some of that potential energy is dissipated into the thermal energy, right? So that's why you are decreasing it, okay? So then the potential energy decreases, that's why. So then potential energy then increases whenever the charge passes through a battery from a negative terminal to positive terminal. Okay, so that's why whenever you go from negative terminal to positive terminal, so basically you go in that direction, you always increase, right, your potential. So that's why, you know, the delta V for this guy here is plus EMF because it increases by that amount of EMF, right? So when applying Kirchhoff's second rule, imagine traveling around the loop and consider changes in electric potential rather than changes in potential energy. So that's why it's easier to think of potential change rather than potential energy. So that's why when I did that equation, I did that in terms of changing potential rather than changing potential energy. All right, so again, summarize everything. So what you have here is this. So following sign convention apply when using second rule. So charges move from high potential end of a resistor toward the lower potential. Because for example, see, if this is my circuit, see the current gonna be in this direction, right? That means current goes from A to B. See, A connected to my positive terminal, B connected to my negative terminal. That means by default, I'm going from higher point potential to a lower point potential. So that's why my potential would decrease, right? So let's say here is 10 volts, here is 0. Then you can see, right, delta V is VB minus VA. Well, it's 0 minus 10 volts. Well, I get negative 10 volts. See, it's a negative potential. I have a drop of potential. So that's why one of the things we're going to do here is look at if your loop direction, so let's say this is my loop direction, matches my current direction, that means I'm traveling from point A to point B rather than from B to A, then I get that. That means, for example, here, if I'm going from A to B, then my delta V here is equals to negative IR. But if I would go like from B to A, my delta V then would have been positive IR, okay? Because you can see, right? So this is for this one, right? So if I'm looking at delta V going from A to B, that means my final point is A and my initial point is B. So I'm gonna get then 10 minus 0, so I get 10 volts. See, positive 10 volts, right? So I gain it. So that's kind of, you know, the idea for the potential difference. Again, it depends on which direction you are traveling, right? So here, then the other example that I was mentioning, if you go from B to A, or something like this. So let's say if the, you know, if you're going such way that you're going in a way like opposite direction of the current, right? So this is not like B to A like I have. Here the current is switched the direction, but the idea here is this, right? So see the current here is to the left from B to A. That means VB is, for example, 10 and VA is 0, right? But let's say if you're going from A to B as the direction of your loop, then you go B as your final, A as your initial, so the delta V here is gain. So that's why whenever you have this, there's a delta V of plus IR. Again, it depends on the direction. So think like this. If you following the direction of the current across the resistor, you drop your potential. If you're going in the opposite direction of the current through a resistor, then you gain a potential. Try to kind of maybe remember that. All right, so then this is for the EMF source. So you can see, right, if our direction that direction of the loop is from A to B, which is from, negative terminal to positive terminal, then potential difference across that is, plus EMF, which means that potential will increase by the amount of the EMF value, okay? But let's say if we're traveling, over here, right? If you're traveling from A to B, but you have A is the positive terminal and B here is the negative terminal, then what we get here is we get decrease of potential by the amount of that EMF, right? So those are the rules. They're relatively simple once you do, let's say, a couple of examples. There are simple rules and you should be able to, if you follow them, even the more complicated problems or circuits can be solved by using this. And one of the things we're going to see here is some of the circuits then can be broken down into different loops. So you might have multiple loops in the circuit, But as long as you're following the rules of the Kirchhoff, the Kirchhoff like junction rule and Kirchhoff loop rule, you should be able to solve those problems. All right. So again, use the junction rule as often as needed. Whenever there's a junction, right, use the junction rule. And your more complicated circuits can then be break down into several loops. So you might have, like, let's say, well, for example, here's a circuit. So then what I can do here is I can say, okay, so there's a one loop over here in that direction. Maybe there's another loop over there. This is loop one, then this is loop two. So I can have two loops, right? So then what you have here is, see, this is resistor one, resistor two, resistor three. So when I'm using loop one, what I have here is this. This is my loop one, which is resistor one and resistor three. Okay, I can have that as my loop one. And then when I'm using loop two, it's just resistor two and resistor three. That means by breaking down into several loops, I can, minimize or minimize some of the device elements I have in my loops. I can also take, a loop like this around the circuit from outside, which goes from EMF, R1, then R2, and comes back. Eliminate R3 because that's not, that's inside the, the circuit. So I'm only looking at, so let's say if this is loop 3, right? I'm only looking at the outside of the outside circuit elements. So there are a number of things we can do. All right, so generally speaking, right? In general, the number of times the junction rule can be used is one fewer than number of junction points in the circuit. So that's kind of like, one thing we can do. And then the loop rule can be used as often as needed, so long as a new circuit element or a new current appears in each equation. Because one of the things we have here is every loop gives you an equation. So if you need to, let's say, solve for 3 unknowns, well, you need 3 equations. If you need to solve for 2 unknowns, you need 2 equations. So that's why one of the things you want to do here is, depending on how complicated your circuit is, try to set up as many loops as you need. Because remember, junction rule is 1 equation. And then you can have, let's say, 2 more loop rules, right? 2 more loop equation. So you have 3 equations, you can solve for 3 unknowns, okay? So that's one of the things we can have. More unknowns you have, more equation you need. So that's kind of like the idea. All right, so kind of, there are some strategies on how to approach this type of, let's say, Kirchhoff rules. So conceptualize, study the circuit diagram, and make sure you recognize all elements in the circuit. You have a resistor, you have a EMF, you have a capacitor, and things like that, because the Kirchhoff rules can be applied to circuits with just a resistor, or resistors and capacitors, or resistors, capacitors, and inductors, which we're going to see later on. So you can always use this. So determine whether the circuit can be reduced by means of combining series and parallel. Basically, is it a simple circuit, or is a not simple circuit where you have to apply Kirchhoff rules? Because Kirchhoff rules can be applied to any type of circuits, simple or not. But obviously, if it's simple, you can reduce it to the equivalent resistor quickly. You don't really need to apply the Kirchhoff rules. So this one says, assign labels to all known quantities and symbols to all unknown quantities. And you will see that in the example. So basically, one of the things we can do here is quickly look at how many devices you have. Then you do your loop equation. And then in the loop equation, right, instead of writing delta V's, you want to write, let's say, EMF1 plus IR1 minus IR2 and things like that. It's easier to do it in terms of like that. And whenever you have a values given, you can do that a little bit quicker by just applying the value. So let's say if you have 5 ohm resistor and then you have an unknown current going through that, remember the potential difference for, let's say, delta V for this guy is just I times R, right? Current times resistance. But let's say your loop is going from this point A to point B. That means it's technically negative. So you can say then delta V is equals to, well, the current is unknown, but we know the resistor, so you can say minus 5I. So you can kind of write it like that, more numerically, to make it a little bit simpler. So minus 5I means that 5 is a resistance value, I is the unknown current, and then it's easier in the calculation later on. Okay, so you're gonna see, right? So you kind of apply those and set up your equation, and then pretty much calculate. Again, make sure during the, at home, go over this, rules much more carefully, try to read them, try to understand them, and then you can use that for the homework and, let's say, recitation and things like that. Anyway, so this kind of talks about that in terms of applying, how to apply, how to calculate, and you will see that in this example that I have. All right, so here's not a simple circuit, because you can see, right, we have, three, let's say, EMFs. And one of the things I have here is, so this guy here, 5 ohms, see, this is, is not in parallel with this or series. So same with this one, right? So you can't say that this is parallel to that and things like that, because there are batteries involved. So if we didn't have EMF, those EMFs, right, you could have just easily said, okay, so this one is, let's say, simple circuit, add them together and you're done with that. But we can't really do that right now. So, but one thing we have here is we have a circuit that more or less has, let's say, 5 resistors and 3 EMFs. So 5 resistors, 3 EMFs, and with those values given for the resistors, right? Remember, we can kind of simplify how we write the Kirchhoff rules, and you have current 1, current 2, current 3, and those current values at this point, let's say, not given to us. That means we need to set up those Kirchhoff rules and try to find then this unknown current 1, current 2, and current 3. From here, by just looking at this, what it's asking, you have 3 unknowns. That means you know for sure right now that you need at least 3 equations, right? 3 unknowns, 3 equations needed. One thing you can see here, there are 2 junction points. Here's junction point A, here's junction point B. Remember, junction point means that there are multiple paths from that. So in a way, one thing you can do here is when you set up your junction point or junction rule, you can just use, let's say, any of those junctions, right? Because, they're all either A or B is in terms of I1, I2, and I3. Okay. All right, so here's what we do then. So you can have, let's say, in this case, technically up to 3 loops. All right, so you can have a loop right here. Okay, so that can be, all right, let's say your loop 1, okay? And then you can have another loop right here. Let's say that could be your loop 2, okay? And technically you can also have another loop like this, which is around, right? And that can be, let's say, loop 3. Now, how do we choose the direction of those loops? Well, the way I always do, I try to choose the direction of the loops to match the direction of the current. Because remember, if you're going in the same direction as current, you always know that you're dropping the potential in the resistors, right? So that means I'm gonna go ahead and choose counterclockwise for loop 1, okay? Counterclockwise for loop 1. And maybe like, let's say, see in terms of loop 2, I don't know, like let's say again, counterclockwise for loop 2, okay? And I'm gonna start with those loop 1 and loop 2, and then if I need, I can go back and maybe do loop 3 as well. But let's start with loop 1. Here's my then loop 1, okay? So I'm gonna set up then the equation. See, for the loop 1, let's see what I have. In loop 1, I have 1, 2, 3, 4, and 5 devices. That means I ignore, this 5 ohm and this 36, volt EMFs. Oh, sorry, I missed this guy over here, right? So I have 1, 2, 3, 4, 5, 6 elements, okay? So 2 EMFs and 4 resistors, okay? And I need to then do the potential difference or the drop or gain, using from that. So I'm gonna then start from this point A. I'm gonna say, okay, so this is my starting point, and I'm gonna go and find the potential difference across each one of them. So let's say I start from A and I'm gonna go counterclockwise. That means first I'm looking potential difference across 11 ohm resistor, then 12 volts, and 7 ohm, then 5 ohm, and so on and so forth. All right, so let's again start from point A and go counterclockwise. Well, first I look at this, let's say this resistor, 11 ohm resistor. Well, one of the things you can see here is this. We are given 3 different currents, and here's current I1. See, this current I1 goes from junction point B, so here's I1, all the way to junction point A, but only through that top path. That means the top path of my circuit has current 1 going through there. But going from A to B through the middle path, I have I2. And from A to B through the bottom part, I have then I3. So you have to be careful here, because I1 only through the top path of my circuit. So basically this is the direction, right? This is what the I1 has. I1 goes only through here, okay? And when I'm looking at the 11 ohm resistant, I have I2 going through that, okay? And you can see, right, my loop goes in the direction of the current, right? Because I'm going counterclockwise. That means if I go to the direction of that means if I'm going like this, that's my loop, and it's in the direction of the current through that resistor, then I have the drop of the EMF. Drop of the potential. And the drop of the potential is equivalent to the resistance times current. So I can then write this as 11 times I2. Okay, so 11 times I2, because 11 ohms times I2 as a current, that's my potential, right? And it's a drop, so I can write it like that. Then if I go then through a 12 volt EMF, I can see that I'm going from negative to positive terminal. So I can say it's a gain of 12 volts, right? Because I'm going from negative to positive. Again, you can go back, you can stop and go back, to look at all those rules. If you, not able to follow me, go back and look at those rules and come back and look at it again. But, negative 11 I2 for the resistor, and then plus 12 volts. And if I continue, then I get negative 7 times I2, because here, you can see, right? So if I'm talking about this one, again, the current I2 going like that, and I'm going in the same direction as the current, so I have a drop of potential, right? So again, I get to the junction point B, and I continue, going through that loop. Now again, here, now I'm dealing with I1. So when I go through this 5 ohm resistor, I am dealing with I1. I1 going in the same direction as my loop. So then I get minus 5 I1, because I get the drop of that. And then if I continue, I go through that EMF of 18 volts. Again, I'm going from negative terminal to positive terminal, so I gain that 18 volts. And finally, I go through the 8 ohm resistor to get to junction point A. Again, I'm going in the direction of the current, so it becomes minus 8 times I1, and that's equals to 0. All right, so this is my loop 1. Again, hopefully you're able to follow. If not, go back and look at the rules and come back and try to, watch it again. So that's my loop 1. I can simplify this, right? Because, what I have here is that I have I1, I have 12 volts, I have 18 volts. I can add those things together, remember. So, I also have I2 and I2 over there, right? I can kind of, combine them. So, and what I get here is, 12 and 18 together gives me 30 volts, right? And then negative 7 I2, negative 11 I2 gives me negative 18 volts. Negative 18, I2. And then from here, I get negative 5 I1, negative 8 I1. I get negative 13 I1. And if I add them all together, I get 0. So in a way, I can simplify this by moving, let's say the current to the other side. So I can simplify this to the 13, I1 plus 18 I2 equals 30. All right, so I get, I get that. And that's just my loop one again. All right. So same way, right? So hopefully you were able to follow. Same way I'm gonna do my loop two. Okay. So my loop two then considers the bottom circuit, right? So where I'm going clockwise. So technically, again, I start from this the point A, and then I can kind of go clockwise from that, right? So if I first go through the 5 ohm resistor, but there's an I3 over there. So it's going to be negative 5 I3. Then I'm going through the 36 volt EMF, and I'm gaining because it's going from negative terminal to positive. So plus 36 volts. Then here I go through the resistor, 7 ohm resistor, in the opposite direction of the current. So then I have plus 7 I2, and I go through the EMFs 12 volts, but from positive terminal to negative terminal. So I have negative 12 volts because I lose potential as I go through the positive terminal to negative terminal. And I go here again in the opposite direction of the current for the 11 ohm resistor. So then again, I have this is then negative 11 I2, and that's equals to 0. So kind of combine them together. What we end up with here is, again, here's my equation for loop 2 is 18 I2 minus 5 I3 equals then negative 24. All right. So that's our, equation for this. Okay, then what we get from here is you have two equations. Remember, we have three unknowns, I1, I2, and I3. I already have two equations, and I have I1 and I2 and I3 there, but I need one more equation to work with. Well, that equation 3 then going to be the junction rule equation. So let's say, for example, if I take junction A, one of the things I can see here is for junction, let's say this is junction point A. So here I have I1, here I have I2, and here I have I3. So this tells me that any current goes into the junction point is positive, anything coming out of the junction point is negative, means it's I1 minus I2 minus I3 equals 0. And that's my equation, which then what I can do here, I can represent this in terms of, let's say, I3, because one of the things we're going to do here is you have three equations, three unknowns, and you're going to have to do the substitution. So then let's say I3 is equals to I1 minus I2. So that means, that's basically one of the substitutions we're going to do. Okay, so I3 equals I1 minus I2. All right, so then what we have here is, and let me write it down here, we have three equations. Okay, so here's what equation 1, 13 I1 plus 18 I2 equals 30. Then we had 18 I2 minus 5 I3 equals negative 24. And then equation 3, I3 equals I1 minus I2. All right. So what I'm going to do here is this. So let's take this I3 and substitute into that equation 2. Okay. That means what I get here is this. And let's multiply, for this equation 3, multiply both sides by negative 1. So then we get 5 I3 minus 18 I2 equals 24, right? If you multiply by negative 1. And then I'm doing a substitution where it becomes 5 times, instead of I3, I put I1 minus I2. Then minus 18 I2 equals 24. That means this equation 3 now becomes 5 So 5I1 minus 5I2, then minus 18I2 equals 24, which we can see, right? And I can combine those two together. Becomes 5I1 minus 23I2 equals 24. All right. That means what I did here is I eliminated I3 pretty much. So then let's say this is my modified equation 2. So now I have two equations. Here's equation 1 in terms of I1 and I2. And here's modified equation 2 in terms of I1 and I2. Now I can work with those. Okay, I can work with those. Because one of the things I can do here is if I come back to this modified equation 2, I can then solve for I1. See, I1, let's say 5I1 equals 24 plus 23 I2, right? And let's say divide this by 5. So that's my I1. Then I go and plug in this into equation 1, right? So I have 13, but instead of I1, I write this, 24 plus 23 I2 divided by 5, then plus 18 I2 equals 30. So I do this. And you can see right now my equation 1, this, equation 1 with I1, substituted in terms of I2. In this equation, I just have one unknown, and that's I2, okay? All right, so that means, I can just do some more algebra from there, right? So let's say, if I plug in this in, like do all the calculation, I'm gonna end up being able to calculate I2, right? So the algebra is in the notes, so you can be able to follow that. So let's say if I calculate, I'm gonna get an I2 of negative 0.416 amps. So I got this. That means this is the value of I2. Now, all I have to do here is take this value and plug it into that equation for I1. I calculate that, so I can find I1 to be 2.88 amps. That means now I have not only I2, but also I1. Then I can go to this equation, for the junction rule. So, and then calculate I3, which is I1 minus I2. So I1 minus I2, I can calculate that to be 3.3 amps. All right. That means we calculate I1, I2, and I3. All right. So positive I3 means that direction given in the circuit is correct. Positive I1 means the direction given in the circuit is correct. But direction for the current 2 is incorrect because we get a negative value. That means in a way, if I have to go back in the circuit, one thing I will see here is that, direction of this current 2 has to be changed. That means this has to be in this direction. Okay, this has to be in this direction, which should make sense because, see, what we did here, we calculated that I1 here is 2.88. I3 here is then 3.3. Okay, and obviously you can see that you cannot have I1 coming in 2.88 and splitting into 2, and one of them is 3.3, which is larger than I1. That means instead what we have here is I1 and I2 going to the junction point, where I2 here is 0.416 amps. And then those two then combine into I3, which is 3.3 amps. All right. So that's kind of like the, the way you would solve problems like this. All right. Okay. So the next concept we have in this, which is the last concept from this chapter, is the RC circuits, where we combine resistors and capacitors in the same circuit. Right. So remember, one of the things we have here is for the capacitors, right, is that the capacitor is a device that can, allow us to store energy. And then a resistor is a device that can allow us to dissipate energy. So, and generally one of the things we have here is in the RC circuit, right? We get this kind of like this time dependence, okay? So things don't happen kind of like instantaneously. Like let's say, whenever you don't have a capacitor, you can assume that as soon as you turn on the switch, the current in the circuit with just a resistor, it's almost instantaneous. Even though it does take, you know, a few microseconds or nanoseconds, but it's almost instantaneous for us. But whenever you have a capacitor in the circuit, well, things actually slow down a little bit. So, and one of the things we're going to be able to do here is look at, you know, circuits like that. So for example, here we have an RC circuit because we have a resistor and a capacitor together, okay? And here's one thing we have. So for example, we have an EMF, and then here is kind of like one of those triple switches. So you have a switch that can go to point A or to point B. See, whenever the switch goes to point A, then you have a capacitor and a resistor, which are in series, right? Then also connected to the battery, okay? But then when the switch is thrown to B, then you can see, right? Then capacitor and the resistor together is disconnected from the battery, okay? That means there is no battery, you know, connected to capacitor and resistor when the switch is connected to point B. So kind of like, you know, it's a way of controlling, let's say, if you want battery to be included or not, okay? So now what we have is this. So it says, assume the capacitor in the circuit is initially uncharged, okay? That means that you have a uncharged capacitor sitting there and it's not connected to battery because the switch is open still, okay? So there's no current while the switch is open, okay? So then what we do here is this. Then if the switch is thrown to position A at t equals 0, then obviously you have a closed circuit. So as soon as what we have right away, right, the EMF produces current, okay? But one thing, if you remember from the capacitor chapter, is this. So this EMF is equals to, so remember this, if you look at, you know, let's say your loop rule, right? So there's an EMF, there's a capacitor, and there's a resistor, okay? So then EMF is the total voltage, and it will be distributed to capacitor and to resistor. Voltage across capacitor plus voltage across resistor, okay? But one of the things we have here is at t equals 0, when you just close your switch, and then you have just that, you know, let's say the current running in the circuit, well, the voltage across capacitor is initially 0. Remember, because the voltage, that there are no charges, it's still uncharged at a t equals 0 when you throw the switch to A, there are no charges on the capacitor. So it has no potential difference. So technically at t equals 0, this is 0. Voltage across resistor is independent of that. That means at that instant, resistor has all the, you know, basically potential. That means the voltage across the resistor is equals to EMF, okay? So that's kind of what we get initially at t equals 0, okay? So you can see, right, that the charges begin to flow, setting up a current in the circuit, and the capacitor begins to charge. As the plates are being charged, the potential difference across capacitors starts increasing. All right, so now as a function of time, it starts increasing. So let's say at later time, I don't know, maybe I don't know, like when, right, it's almost there. So let's say t equals, I don't know, like 0.5 seconds or something like that. You know, EMF now is VC plus VR, okay? Remember, EMF value doesn't change. So let's say if it's 10 volts, and when at t equals 0, voltage across the resistor was equals to EMF, that means voltage across the resistor was also 10 volts. But as a function of time, voltage across capacitor starts increasing. Well, you cannot have 10 plus something else, right? Because the total that battery gives you is 10. That means voltage across capacitor starts increasing, or voltage across the resistor starts decreasing, because now capacitors start taking more and more of the, you know, its share. But one of the things we have here is that you can see, right, the value of the maximum charge on the place depends on the voltage of the battery, right? So, so then once the maximum charge is reached, the current in the circuit is zero. Why? Because this capacitor voltage is going to increase so much that it's going to be equals now to 10 volts, which means that the resistor basically doesn't get anything else. And one of the things we have here is then as soon as you have the voltage of the capacitor matched voltage of the EMF, the current goes to zero because capacitor is fully charged. Okay, right? Because the potential difference across capacitor matches the supplied battery. That means what we get here is current goes to zero. That means as a function of time, this current here, which was maximum in the beginning, starts decreasing all the way to zero. And it takes time, let's say a few seconds or milliseconds or microsecond, right? But it's, you know, it starts with maximum value and then it starts decreasing. Okay, so one of the things we can do here is to find that current. We can apply Kirchhoff's rules because I have 1, 2, 3 devices in the circuit, right? And, you know, one of the things I have here is Kirchhoff rule tells me that if I start from this, let's say some point A over there, and I go through the EMF, I gain of EMF. As I go to the capacitor, you can see I go from positive to negative, so I lose, you know, so basically the potential. What is the potential loss? Remember, V for the capacitor is Q over C, right? Or, you know, we can like do it like this. Is Q over C, that's the equation. So that's why it's minus Q over C. And as I go through the resistor, since I'm going in the direction of the current, then I have a drop of IR. And then this is my loop equation. So let's say this is my loop equation. You know, gain from EMF, but then it's, you know, some of that potential is lost across the capacitor and then lost across the resistor, right? And if I add them together, I get zero. All right, so now one of the things I have here is this. You can see, right, Q and I are instantaneous values that depend on time, okay? So here, this I over there is basically, you know, we're talking about instantaneous current because current is changes as a function of time. Same thing is here. Q is also instantaneous. So that means this equation is for some, you know, instant of time because I would, you know, change, Q will change, right? So that means, see, the Q will change until it becomes, you know, total Q. You know, I, you know, starts with maximum and it's going to go and become zero at the end, right? So that's why those are time-dependent values in this case. All right, so you can see, right, at the instant the switch is thrown to position A at t equals zero, the charge on the capacitor is zero, and the initial current is a maximum and is given by this equation. Why? Because remember, EMF equals, so using the ohms, you know, the Kirchhoff, right? EMF minus Q over C minus I times R equals zero. Well, remember, to start with, there are no charges. So this is zero, means that EMF is equals to IR, right? Kind of following that. And then from here, you can say I is equals to EMF over R. But this happens at t equals zero, which means we're dealing with the maximum current, okay? So that's kind of what we have. So at this time, the potential across the battery terminals appears entirely across the resistor. Okay. So then when the capacitor charges to its maximum, you can see, right, when Q goes and becomes its maximum, there are no more charges, right? Because, you know, it's maximum already, it's full. And the current goes to zero. And the potential difference from the battery terminals appears entirely across resistor. So, capacitor. Resistor basically no longer operates at that instant, okay? And one of the things we have here is, well, now you can think like EMF becomes Q over C minus I times R equals zero. So this is at that final time. So what happens at the final time? Well, there is no current. So this is zero. That means EMF minus, and then Q is equals to the total charge. So Q over C, EMF minus Q over C equals zero. Or you can see, right, EMF equals Q over C. And then using that, you can find that maximum charge, which is C times the EMF. All right. So Q equals C times EMF, you can find the maximum charge. Again, because at this time, whatever that final time is, right, the current here is 0, and then Q becomes the total charge. So you can kind of find that. Again, what we did here, we look at this, you know, t equals 0 and some final time, whenever it is, right? But at the final time when current equals 0. So we looked at those extreme points. But at the same time, you know, you have any, you know, things in between. So let's say, what is the current somewhere between those times? Or what is the charge somewhere between those times? And so technically to get that, then we have to go and derive equation for current as a function of time. Because I know for sure that at t equals 0, my current is at maximum, right? And at the final time, my current here is 0. Those are my two extreme points or two extreme times. But anywhere in between, current is neither maximum or 0. And I want to be able to find that. So we will be able to set up an equation that I can use to find that. Well, it's not an easy equation to derive because we're going to have to use differential equations for that. Because one of the things we have here is, right, so let's say this is pretty much coming from that equation, right, EMF minus, you know, let's say Q over C minus I times R equals 0, okay? So in a way, let's say you can see that if I'm setting up this equation, so if I move IR to other side and write it like this, so IR equals EMF minus Q over C. And if I divide both sides by R, so I get that, right? So let's say current is equals to EMF over R, then minus Q over RC. Okay, so that's this equation over there, because remember, current is nothing but dq dt, right? So then I can replace it like that. All right, so then what we do from here is we just basically separate differential equation and just, you know, use this equation to set up the let's say the time varying equation for the current and for the charge. And, you know, basically to do that, we're just gonna have to do some, you know, derivation, right? So for example, in this case, take this equation, right? And then we can, you know, kind of like simplify this to Q minus C times EMF over RC, right? So basically simplify to that. And then rearrange it where in one side you have dq, in other side you have, you know, dt. So basically going to be dq over Q minus C times EMF. Basically you want the term that has a Q with a dq, and then anything else with a dt. So move the dt to other side. So you end up with negative 1 over RC dt, okay? And then we're gonna then integrate both sides, okay? So integrate both sides. This is basically going from 0 to Q, okay? And this one going from 0 to T, okay? So those two integrals. And when you do the integration, right? So pretty much we're gonna end up with, you know, ln Q minus C times EMF over negative C times EMF. And here we just, you know, the right side is much simpler. So integral of dt is just t. So negative t over RC. Okay. Again, a little bit more, you know, derivation, right? Taking the, you know, e on both sides, right? E, like, you know, like let's say natural e, right, on both sides. We end up with this equation q as a function of time, okay, which is equals to C times EMF and then 1 minus e to the negative t over RC. That's the equation for that. That means this is the equation for time-dependent charge, okay? So again, so let's say one of the things you can see here is, so I have Q as a function of time equals C EMF, then 1 minus e to the negative t over RC. And this equation allows you to see that this type of equation, right, when you have 1 minus e to the negative t RC, that means if you looking at the Q as a function of time, you know, it increases. You have a graph, right? You can see it increases like that, okay? So this represents the increase, okay? A logarithmic or increase for the current for the charge, okay? Remember, this term itself is equals to the Q max, right? So that means, one of the things you can do here, you can calculate this in terms of that. So Q times 1 minus e to the negative t over RC. This value RC is also known as a time constant tau. So we can also, use that, which represents how long it takes for the let's say charge to increase about 63% of its value. Okay, so this tau, this RC actually, has units of seconds and represents some kind of time constant. All right, so similar way we can, go and derive the current. If I go to this equation, right, and remember, if I take the derivative of this, I'm going to get current. That means I come back into the derivative of that, right? And if I do that, I get this equation, okay? Where, I as a function of time equals E over R, so EMF over R, and that's basically nothing but I max, right? And e to the negative t over RC, which actually allows us to see that, the difference between, so you have two different type of equation. Q is equals to maximum value times 1 minus e to the negative t over tau, RC replaced with tau. And then the current as a function of time is equals to its maximum value, then e to the negative t over RC, t over tau. See that because this is 1 minus e to the negative t, and this is just times to that e to the negative t, this represents increase, this represents decrease. Okay, so you can see, right? This is the graph for the increasing charge. As a function of time, it is increasing. And then the next slide, you're gonna see that this represents decreasing current, exponentially as a function of time. That means you start with the maximum current as a function of time, you're decreasing, where again, you can see, right, after a time interval equal to 1 time constant tau has passed, the current is 36.8% of its initial value. So we kind of have that, right? So this is just to charge the capacitor, okay? So all this process just to charge the capacitor, okay? So then what happens when you throw the switch from A to B? Well, when you throw it from A to B, then battery is no longer part of the system. Okay, so you have just this is your loop. Well, one of the things we get here is before we throw the switch from A to B, we charge the capacitor. And the capacitor has, potential difference. It has full charge, right? So it can act like a battery. And it has a current, this is positive terminal. It's going to have a current going around in this case, let's say counterclockwise direction. But one of the things we have here is that as the current goes around the circuit, and because there's a resistor, the energy starts going to dissipate. But capacitor is not a battery, it's not an EMF source. It cannot maintain the potential difference. That means whatever current you start with, that current or potential difference is going to start decreasing as a function of time. Charges across capacitor is going to start decreasing as a function of time. Because again, capacitor starts losing its charge, starts losing its potential because it cannot, through those chemical reaction, right, reinforce itself. So that's why one of the things we have here is, let's say, as soon as you throw this switch to B, the capacitor at that instant, at t equals 0, it has basically maximum potential, right? So remember, which was equals to the EMF. This is the maximum, but it's at t equals 0. And then at t equals 0, you also get the maximum current, right? You also get the maximum current, and you get the maximum charge. So that's right. So the potential difference Q over C exists across capacitor, and there is 0 potential across the resistor. Okay, because I equals 0 when when it's complete. When it's completely charged. But when the switch is thrown to position from B to B, right, at t equals 0, then capacitor begins to discharge through the resistor. Okay, so this was before we switch to B, and this is right after we switch to B at t equals 0. Okay, so then at some, again, one of the things we do here, right, you can see that in this equation, we have only capacitor and a resistor. So, and there is a discharge from the capacitor and the resistor. So we basically have negative QC minus IR because both, have a negative potential. We lose potential as it constantly go around in a circuit. Okay, there is no EMF anymore. Okay, that means one of the things we can do here is we can look at in terms of just this particular, circuit. Okay, and we can use this to derive, let's say, what we get. So you can see, right? So from here, what I get here is this, R times I, or like let's say negative R times I equals then Q over C by moving this to the other side. So then negative R, well, I is dQ dt, right? And it equals to Q over C. Well, there's a Q over there. We want to move the Q to the other side where there is a Q also. So this becomes then dQ over Q, and then R moved to the other side with the dt, so it becomes negative 1 over RC dt. And then we integrate both sides from 0 to Q. This is from 0 to T. And we end up with, again, both of, this left side going to be ln of Q over, maximum Q, right? Because we go from, remember, we start, so sorry, it's not 0 to Q, it's from maximum Q to some Q. And then on the right side, we just get negative T over RC. Okay, so if I rearrange this, I get an equation Q as a function of time equals, so this guy over here, right? Again, taking the E of both sides. So this becomes Q as a function of time equals maximum Q, then times E to the negative T over RC. But again, RC replaced with tau, let's say in this case. And taking the derivative of this one, I can get then current equation, where current as a function of time equals negative Q over RC, then E to the negative T over RC, or just, okay, so let's say RC. Otherwise, you can replace RC with a tau, but that's kind of what you have. So you can see, right, we get two equations. Q as a function of time. And again, you can see here, it's an exponential decrease. So you start with maximum Q, as a function of time, you decrease. How about the current? Same thing. You start with the maximum, and then it decreases exponentially. Because capacitor, whatever charge it has, is going to discharge. And whatever current it produces, it's also going to dissipate as a function of time. Okay. All right, so here's one example, and pretty much this is the last example of this chapter. So we'll do this. And this example, again, considers, RC circuit. So suppose the current in a conductor decreases exponentially with time according to the equation. And, we're given this time-dependent equation for the current, right? Where I naught is the initial current at t equals 0 and is a constant having dimension of time. Okay. So consider a fixed observation point within a conductor. Okay. So then how much charge passes this point between t equals 0 and t equals tau? How much charge passes this point between t equals 0 and t equals 10 tau? Okay. And what if, how much charge passes this point between t equals 0 and t equals infinity? All right, so basically what we get here is this, right? So we're given equation for the current. So again, this is I equals maximum, right? And then E to the negative T over tau. Okay. And one of the things, if you remember, right? So the current here is dQ dt, right? Or, let's say dQ dt. Okay. So from here, then I can, remember, I want to, look at in terms of how much charge goes through. So dQ here is equals to I dt. Because one of the things I want to do, I want to find a, equation for the charge as a function of time. Okay. So dQ equals I dt. All right. So what we do here is, well, integrate both sides. The left side is simple enough because this goes from 0 to Q. And it's basically just Q. On the right side is an integral I dt. Remember, we want to go from 0 to tau, right? When t equals tau. Well, we're also given that, the current here is I naught e to the negative t over tau dt. Okay. So it's going to be then, integral from 0 to tau. So negative I naught tau. Okay. And e to the negative t over tau, negative dt over tau. And which is kind of like a trick that we can use to, rearrange like that. So basically, we're multiplying this by negative tau over tau, right? You can see, right? Tau, tau, so negative, basically multiplying by -1, which, we're multiplying by 1, and that's just, negative, tau over tau. So like, let's say. All right, so, and from here, one of the things we can do here is if we perform this, we can then get Q as negative I naught tau e to the negative t over tau minus e to the 0. Okay, so those are basically the limits. And we get I naught tau 1 minus e to the negative t over tau. Okay, so we get that. So this is our equation that we derive. Then we look at part A, which says, okay, so how about when t equals tau? That means you take this t over here and replace it with tau. So Q as a function of tau, right? The time when time equal, do it like this, when t equals tau. So I naught times, tau, then 1 minus e, and just basically negative tau over tau, which becomes -1. All right, so we calculate, we get 0.632 I naught times tau. Part B, we just do, this is 10 tau. All right, so the same thing, right? Q when t equals 10 tau. And again, so plug in same thing, we're gonna get 0.99995 times I naught tau. Then for part C, when t equals infinity, then if I do Q when time is equals to infinity, well, remember, so this is basically, I naught times tau, and this is just 1 minus e to the infinity. Well, e to the infinity is 0, so this just gives me I naught times tau. All right, so that's those are my then, for final answers. All right, guys, so we are, concluding this chapter. Then I'm gonna then later on upload chapter 22 slides. So for now, we're gonna be using this for the next, discussion and recitation.